Welcome back to the Explainer. Today we're focusing exclusively on Section 7.2, How is Periodicity Represented? We are diving straight into the ultimate gateway of hearing, which is the auditory nerve. This is the exact biological threshold where physical sound waves vibrating in the air suddenly become electrical signals in our minds. It's a fascinating transition.
So here is our roadmap for this explainer. We're dividing our exploration into two main parts. First, we'll look at Section 7.2.1 on pure tones, and then we'll escalate to Section 7.2.2 on complex tones.
Okay, let's dive right into this. I want to start with a quote from our source material because it sets the stakes absolutely perfectly. It reads, "Any information about a sound that is not present in the auditory nerve is lost forever as far as the auditory system is concerned." Just think about that for a second. If the auditory nerve misses a detail, your brain will simply never ever hear it. The fidelity of this neural representation is literally everything.
Moving into Section 7.2.1, pure tones.
Now, you might be wondering why we start with pure tones. Well, because they are so mathematically simple, they make the perfect testing ground for figuring out how our brain first begins to code pitch. But to really understand how we process these tones, we first need to define a foundational concept, and that is characteristic frequency. Think of this like a tiny biological tuning fork inside your ear. It's the specific frequency at which an individual auditory neuron is most responsive. So a pure tone is going to cause a specific set of neurons tuned to that exact frequency to fire at their absolute highest rates.
For a long time, scientists have debated exactly how the auditory nerve communicates frequency to the brain, and it turns out we have two really interesting contenders here. On one side, we have the rate place code. This is all about where the firing happens. A neuron fires fastest when a sound matches its specific location, its characteristic frequency. On the other side, we have the temporal code. Now, this is about when the firing happens. In this model, neurons actually lock their firing times directly to the rhythmic timing of the sound wave itself.
And this brilliantly illustrates the difference between those two codes, which is pretty striking. On the left, looking at the rate place model, you only see a very subtle shift in the neural excitation peak when changing from a 500 Hz to a slightly higher 550 Hz pure tone. Our brains would have to detect incredibly tiny, sub-decibel changes just to notice the difference. But check out the temporal code on the right. The spike patterns show clear, distinct mathematical timing differences. The actual time intervals between the neural spikes change drastically, going from flat 2 millisecond gaps down to 1.8 millisecond gaps.
So the crucial point here is understanding how this exact timing works, which brings us to a really cool biological phenomenon called phase locking. This is the propensity of neurons to fire at a particular phase of the waveform. They literally match their neural spike intervals to the exact period of the tone. They act like tiny little metronomes keeping perfect synchronized time. Imagine you're tapping your foot perfectly to the beat of your favorite song. Well, your neurons are doing exactly that, just with the physical sound wave.
But that begs the question, which of these two codes does our brain actually rely on to hear a melody? Well, this data is widely considered the smoking gun. This line tracks our ability to discriminate pure tone frequencies. Notice how incredibly sharp our ability is at the lower frequencies, right? But then, it completely breaks down right near the 5,000 Hertz mark. It just so happens that we lose our sensation of musical pitch exactly at the biological frequency limit where our neurons lose their physical ability to phase lock. It heavily implies that temporal coding takes an early, decisive win for giving us the sensation of pitch.
Let's move on to Section 7.2.2, Complex Tones.
Hearing pure tones in a highly controlled laboratory is one thing for sure. But how do these theories actually hold up against messy, everyday sounds like human speech or a musical instrument? A complex tone consists of many different frequencies, or harmonics, played all at once. Notice in the middle excitation pattern how the cochlea acts almost like a prism for the lower harmonics. It neatly separates them out into clear, distinct peaks. We call these resolved harmonics. But as we move up to the higher frequencies, the auditory filters in our ear physically get wider. Because of this, the higher harmonics aren't neatly separated anymore. They just blend together into a smooth slope, and we call those unresolved harmonics.
Let's move to the next visual and see how this builds when we look at neural reactions. Looking at the lower, resolved harmonics, they produce perfectly clear, smooth sinusoidal vibrations on the basilar membrane. Auditory nerve fibers can easily phase lock directly to this nice, fine structure. But looking at the unresolved higher harmonics, they're overlapping. They actually physically beat against each other, forming a complex pulsing wave that's known as an envelope.
Now, this physical blending creates a massive headache for the rate place code. Because these unresolved harmonics are clumped together, the firing rate across the cochlea provides virtually no specific information about the fundamental frequency. Under a strict rate place model, the brain really shouldn't be able to hear a clear pitch from this at all. Yet temporal coding elegantly solves the puzzle. The auditory nerve fibers simply phase lock to the repeating pulse of that envelope we just saw. By tracking the timing of the envelope, the brain extracts the pitch. It's just an absolutely incredible biological workaround.
So, we've built a very comfortable, logical conclusion so far. Pitch relies heavily on the temporal timing of neural spikes, not just the place of the firing. But I have to ask you a bold question. Is temporal coding strictly necessary for pitch? Because what happens next in the research shatters absolutely everything we thought we just figured out.
Now, what's really interesting about this slide is the spectrum from a landmark 2011 study by Oxenham and colleagues, which completely shatters that conclusion. See that dashed line in the middle? That's the 5,000 Hz limit, the absolute biological speed limit where neural phase locking completely breaks down. Yet when listeners were played a set of harmonics that existed exclusively above that line, starting way up at 7,200 Hz, listeners could clearly hear a fundamental pitch of 1,200 Hz. They successfully recognized melodies from a pitch where temporal phase locking is mathematically and biologically impossible. This single experiment literally flips the entire debate on its head. Think about it. If there is no temporal phase locking happening up at those high frequencies, how on earth are we hearing the pitch? Could the pitch of complex tones actually be coded by rate place information for those high-resolved harmonics after all? Does the brain dynamically switch its strategies on the fly? The ultimate mechanism of human hearing remains a tightly guarded secret of the brain. It's a profound mystery that is still being actively decoded by researchers today. So, what does this all mean for the future of auditory science? Well, watch this space.